Today we're going to talk a little bit about forging temperatures in Wootz. Now, previous video we talked about solidification structures and made use of this exact same diagram, which is sort of my rough rendition of a portion of the iron-carbon phase diagram. A little more comfortable here. There we go. Now, again, we're going to assume a 1.5% carbon steel, but this time we're going to kind of work in reverse. Last time we worked our way down as we cooled that ingot, or solidified and then cooled that ingot. Now we're going to work our way up. Talk about what happens as you heat your ingot. So, having 1.5% carbon means that we are hypereutectoid. Remember the eutectoid point, roughly 0.77% carbon. In the low temperature range, the subcritical range, this basically means that you have, at the eutectoid point, you have all perlite. Perlite is a very specific mixture of ferrite, which is pure iron, and cementite, which is carbide. Now, in hypereutectoid steels, like what we're going to be dealing with, you have a mixture of perlite and free cementite, now, or carbide. And essentially, in cementite, the pure iron and iron carbide are arrayed in very fine layers, essentially. And in the, once you reach the hypereutectoid steels, now you have excess carbon. Doesn't fit in the perlite because it's a very set ratio. So you start to need places for that extra carbon to go. You start to form free carbide, or basically like freestanding carbide. That is a structure in and of itself that the perlite then forms around, essentially. So, as we're heating, when we hit the critical, we'll just call it, at roughly 1350 Fahrenheit or 727 centigrade. Got that off my original phase diagram, so thus the very exact centigrade. Phase diagram that I have is in centigrade, so that's why I have approximate values for the Fahrenheit numbers. But in any case, we get up here to critical and enter this zone, which is a mixture of austenite and free carbide, free cementite. Now, so it's basically, as soon as we hit that line, or soon thereafter, we put roughly 0.77% carbon into solution in that austenite. Now, we're dealing with a 1.5% carbon steel, so as it works out sort of conveniently, roughly half our carbon is still tied up as carbide. As our temperature increases, that carbide continues to dissolve until we cross the ACM line, where we transition from austenite and cementite to just austenite. Now, I've mentioned this before, these transitions all take a certain amount of time. This one generally is fairly quick because what you are dissolving is the perlite, and perlite, since it's already a very set ratio, it's like you've got the proper mix of ingredients to make austenite. So as soon as you get the temperature, very quickly the perlite dissolves and you get austenite instead. and that 0.77% carbon is in solution. But these free carbides, depending on their size and how close they are to each other, probably take a bit longer to dissolve. So the faster you heat through this zone, the more carbide you still have as free carbide rather than having dissolved when you cross the ACM line. But let's say we're heating very slowly. We cross this line, and now we have no carbide left. Now we continue up through the pure austenite zone until we hit about 1250 C, which is where we cross into the slushy zone. Anybody who's experienced slush knows that you can have, in terms of, water slush, so ice and water, that lovely mix. You can have a substance that looks solid until you step on it, and then you just, squish right to the bottom. And steel's exactly the same way. All the metals, all of the mixed metals are kind of the same way, where you have this slushy zone of partial liquid and partial solid. So when you first cross this line, you're going to have almost entirely solid material still. So it will look just like it had. There's not going to be a big change of like, ooh boy, look, there's liquid dripping off that. You won't see any liquid. It'll look basically the same, but when you hit it, all of your little grains, there's a certain amount of liquid around them. And so your solid material moves around in that liquid pretty readily once things get moving. You'll get what I refer to as a wet sand fracture, where the material tears rather than cracks. And you'll be able to tell when this has happened, because when you look at your ingot, there's a crack or crevice, but the sides of it are just super rough. When you get a brittle fracture, things will tend to be quite smooth, whereas with a wet sand fracture, you will get a rough, sandy-looking surface. Carbon is not the only possible culprit in this. If you have sulfur in your steel, you will get a hot short steel. And hot shortness, if I recall, it falls somewhere in this zone, about 1000 C. I think it's 980 C, something like that. So some of the old steels that had high sulfur content, you actually could not cross the ACM line and forge. You could cross it, but you couldn't forge at that temperature. So you could have gone above, and then dropped back and started forging. The good thing about this type of fracture is that it can be avoided as long as you don't hit the steel at that temperature, while it's in that state. So if you've overheated your steel, you realize it, and you let it cool before forging it, you should be okay. I'm not going to say you're going to be okay. Nothing's 100% certain. So again, this is where we get into some of that pick your own adventure type stuff. So looking at this, you can see there's some choices about where to forge. The easiest forging is going to be of pure austenite. Having carbides in there stiffens the material. Things move more slowly. Depending on how you're forging or your end goal, you may decide to forge entirely as austenite. Now, if you don't clear the ACM line, one thing that I will note, especially if you have higher alloy material, each time, while you're working in this zone, some of your excess carbon is in solution. And as you begin to cool, that excess carbon starts to form carbides again. If you have a lot of carbide forming elements in your steel, and you're working just in here, you're going to tend to really suck up that carbon onto those elements or right in the vicinity of them. Because remember what I said before, there are a few different reasons for carbides to precipitate where they do. You can have them precipitate on austenite grain boundaries, because where the grain boundaries are, the crystalline lattice doesn't line up perfectly. So you essentially, you get holes or dislocations in the crystalline lattice, so convenient spot to have carbon pop out of solution, make some carbides. Another place that is common is if you have carbide forming elements. They bond more strongly with the carbon, they are more likely to precipitate carbides. And lastly, carbides make really good precipitation points for more carbide. And the reason for that is, again, they don't fit nicely into the crystalline lattice, so you get dislocations around those carbides. So, if you're working entirely in this zone here, you heat and you put a little bit of carbon, or a portion of the carbon into solution, and then you cool and precipitate carbides. There's going to be a self-reinforcing aspect to that the areas where you have carbide are going to get more carbide. Specifically, you're going to tend to get larger carbides. And this doesn't matter, it doesn't matter really if you are dropping below critical each time or not. If you don't clear the ACM line, you'll tend to grow larger carbides. I refer to these sometimes as wolf carbides. Anybody familiar with forestry may have heard of what are called wolf trees. If you're in a forest, you'll occasionally find one tree that is growing huge at the expense of the trees around it. Again, I'm not going to tell you whether that's good or bad, because I want you to have a journey here. But that's what you will tend to get. If you work above the ACM line, or go above the ACM line on every forging cycle, or most forging cycles, you will dissolve more of your carbide each time. But again, it will reform as you cool. So this will tend to get you, for the most part, smaller carbides. You can still get wolf carbides in this scenario. Because the larger a carbide is, the longer it takes to dissolve. So once you start to get large carbides, they tend to be self-reinforcing. This is referred to as Ostwald ripening. The idea that over many cycles, the larger carbides grow at the expense of the smaller carbides. Again, I'm not here to tell you the exact route to take. I can tell you that historically, any route you decide to take, it's already been taken. It's already been done. There are historical blades that were pretty clearly forged almost entirely, never clearing ACM. Some of these had sulfur issues in the steel, so you couldn't forge above ACM. Some of them, perhaps it was a choice, who knows. Other ones pretty clearly got forged above ACM and then back down. I'm going to tell you, though, this is a key piece of information. You may have been told or read somewhere that Wootz needs to be forged subcritical. And I'm going to tell you right now, don't do it. Subcritical forging, not a good idea. Especially, it's one thing to do subcritical corrective forging. You know, you're just heating it up to that very dull red, kind of a black heat, because you want to straighten something. Have at it. If you want to actually start moving the material, don't do it. Subcritical forging, bad. As things are cooling, it's very easy. You know, when you're forging a blade, you know, whether it's Wootz or otherwise, it's very easy. You're forging your blade and the steel's still moving nicely, and you end up going subcritical with it. Well, I'm going to tell you something. You didn't go subcritical. This line moves based on how quickly you are heating or cooling. So really slow cooling, well, criticals, or very slow heating, criticals right where it shows it to be here. Same thing, very slow cooling, criticals right there. Faster you're cooling, the more this line moves. So when you're forging, especially on a thin blade, cooling's pretty quick. Subcritical's further down, or the critical line is further down than you think it is. If, however, you were heating to a subcritical temperature and then tried to forge, you would find that it was a very different material. Sometimes when you're forging on the cooling side of things and go subcritical, steel still feels okay, you know, and then starts to stiffen up. That's when you're making that transition from the austenite structure to the ferrite structure. If you heat to that same temperature and try to forge, you're going to get a very different experience. That steel isn't going to feel good, and it's not going to react well. So if you have heard somewhere, read somewhere, somebody told you Wootz needs to be forged subcritical, that is wrong. It's one of the few really strong statements I'm going to make here. My take on this is that most people have misconstrued the ACM line. And if you have steel that is hot short, it does need to be forged at below the ACM line. And in fact, if it's because of sulfur, which is the main cause of hot shortness, it's an entirely different line altogether. The temperature actually is basically the same all the way across because it's caused by a different compound. But you know, I think that is where the idea came from. But please ignore it. So you can happily forge just in, you know, just topping out in the ACM or below ACM, but you cannot happily forge just topping out below critical. So things to keep in mind from this as you're deciding how you want to forge. Time at temperature makes a difference. If you are, you know, you've crossed into the austenite cementite area, how long you stay there really changes how much of the carbide dissolves, how much carbon goes into solution. That's perhaps even more true as you get up above the ACM line. Again, just like with critical moving based on how fast you are heating or cooling, the ACM line shifts based on how fast you are heating or cooling. You can know for certain that pretty quickly after crossing critical, you've put about 0.77% carbon into solution. And as you continue heating, whether it's fast heating or slow heating, you're going to be dissolving additional carbide. How fast that happens depends on a variety of factors. How large your carbides already are, how much alloying element you have in there. But as you heat, you're going to be dissolving carbide. That becomes particularly true after you cross ACM, which of course, I guess I should clarify here. When I talk about crossing the ACM line, I'm talking about the one on the diagram. The actual ACM line would be wherever you cease to have any carbide. Since carbide takes quite a while to dissolve, you never cross the ACM line. We won't get into it, but carbide can take up to hours to dissolve fully. And this brings us back to our initial ingot structures. If you have the very dendritic primary carbide structure, it could take hours at being in the austenite zone to fully dissolve that primary carbide. In industry, 52-100, which is a hypereutectoid steel. It's got chromium, which is a reasonably strong carbide former, but it's not a super hypereutectoid steel. The initial ingot they soak for about 4 hours at about 1250 and still have not dissolved all the primary carbides before they start rolling. But what they do is they've dissolved enough primary carbides to roll the steel effectively. So that gives you some idea how long carbides can take to dissolve. If you go back and look at the articles written by Pendray and Verhoeven, you will see that they definitely did a roast. So that's sort of the historical term of taking your ingot, heating it to an elevated temperature, and holding it there for an extended period of time. They were aiming to dissolve all their primary carbide and even out their carbon content as much as possible. In their early work, they did what they called a rim treatment, where they actually decarburized a shell on the outside of the ingot. So they had a low carbon shell on the outside of the ingot to improve the forgeability. Later on, they discovered that wasn't necessary as long as they did not have sulfur and phosphorus in their ingots at elevated levels. The sulfur in particular really kills the forging. They were able to get around that by that very long treatment of, I think it was 12 hours perhaps, to decarburize that rim, kind of contain the material for a while during the initial forging stages. The only other thing that I'm going to tell you at this point for forging temperatures, and this refers to the initial ingot, and this is another piece of information that you could get from the articles by Verhoeven and Pendray, is right near the ACM line, there's also a graphite line. And when I've talked about this before, that when an ingot solidifies, you end up with microscopic pores because liquid is larger than solid. So if you imagine your ingot has solidified first on the outside and set your volume, but now your material inside is shrinking, you're going to have some voids in there no matter what. Really slow solidification, you'll get one or two very large voids in the center, but for the most part with Wootz ingots, what you get are microscopic voids scattered throughout. These tend to be right in the same areas where you would form these primary carbides. Those are the IDRs, as Verhoeven calls them, or interdendritic regions. They're the last areas to solidify, therefore that's where the pores show up. Depending on how you forge your steel, or forge your ingot, those pores can either close up and weld closed, they become a non-issue, or they can fill with graphite. If you have voids in your steel and spend a lot of time just below the ACM line, you're going to fill those voids with graphite. And once that graphite's there, it's very hard to get rid of. So what Verhoeven and Pendray did was that their initial forging was at a very high temperature. I believe they have some forging that starts at 1250, but I think that was after doing the rim treatment, creating essentially almost pure iron on the outer shell of the ingot. But it's a good idea to have your initial forging be above the ACM line to close up some of those pores before they can start filling with graphite. So, yeah, and I think that's what we'll cover for now. Again, I will post some pictures that on my Instagram page at PeterBurtKnives that will illustrate a little bit of this, and and again, if you have questions, ask them here in the comments, or swing over to my Instagram page and ask the questions there. I always do my best to answer specific questions. If you say, what temperature should I forge at? That's not a specific question. If you're having an issue, or have a specific metallurgical question about why you might make one choice or another, that's the kind of question I'm going to answer. But I really want this to be a journey for you, an exploration for you, not me giving you a recipe that you follow and don't understand why it works or doesn't work, as is so often the case. So, hope this was helpful, and see you in the next video.